So this proves the first property, which is the upward and downward monotone convergence theorem. Now before we come to the dominated convergence theorem, I will prove the third property, which is inner regularity with respect to compact sets. So here's the statement for the inner regularity property with respect to compact sets. So this says that if E is a Lebesgue measurable subset of RD, then we have this formula that M of E, the measure of E, can be written as the supremum of all compact subsets of E. Supremum is taken over all compact subsets of E of the measures Mk. So let's prove this. So let me first suppose that the measure of E is finite, and we will produce a compact set such that the supremum property is validated. So given epsilon greater than 0, we have to find a compact set K, which is a subset of E, such that ME is less than or equal to Mk plus epsilon. So this will show that ME is the supremum of all these Mk's. So to do this, we use the inner approximation by closed property. So by inner approximation by closed sets, there exists a closed set F inside E such that the measure of E minus F is less than or equal to epsilon by 2. So here I am fixing epsilon greater than 0, and then we use the one of these equivalent properties for Lebesgue measurability to find a closed subset F of E such that measure of E minus F is less than or equal to epsilon by 2. But this is equivalent to saying that measure of E minus measure of F is less than or equal to epsilon by 2 using finite additivity property. And because all these are finite, we can write this, and so ME is less than or equal to MF plus epsilon by 2. Now I am going to use the upward monotone convergence theorem. For the sets Kn, which is F intersection the closed wall with center 0 and radius n. So now this Kn is a compact subset of E for each n greater than or equal to 1, and we also have that F is equal to the union of these Kns as n equal to for n equal to 1 to infinity. So this implies that the measure of F itself is equal to the limit as n goes to infinity of the measure of these compact sets Kn, and so this is by the upward monotone convergence. And this implies that there exists, so by the definition of the limit, there exists a capital N belonging to n such that measure of F, the modulus of measure of F minus the measure of Kn is less than or equal to epsilon by 2, but K capital N is a subset of F, so we can get rid of the modulus sign and so this means that mf is less than or equal to m of kn plus epsilon by 2. But remember that me was less than or equal to mf plus epsilon by 2, but now we have bounded mf by mkn plus epsilon by 2 plus epsilon by 2, and these two epsilon by 2's make an epsilon. So we have found a compact subset of E k capital N such that our supremum condition holds. So this implies that, so this shows that Me is the supremum of compact subsets taken over compact subsets of E of the measures Mk when you have Me is finite. So now suppose that Me is infinite. So then we can again write it, we can write E as the union of sets Ek, k equal to 1 to infinity, where Ek is the intersection of E with the closed wall of radius k with center 0, and so now Mek is finite for each k greater than or equal to 1, and by the upward monotone convergence, again upward monotone convergence, because we have a nested sequence, Ek is a subset of Ek plus 1 for all k. So by upward monotone convergence we have that the measure of E is the limit of these measures Ek as k goes to infinity, and we know that this is plus infinity. So Mek goes to plus infinity as k goes to infinity. Now since each Mek is finite, we use our previous result, as we have proved here that when M is finite, then it is a supremum of the measures of compact subsets. Previous result, to find compact sets kk for each k greater than or equal to 1, such that Mek is less than or equal to Mkk plus 1, say. So because of the supremum property for inner regularity property for measures of Lebesgue measurable subsets of finite measure, we have this inequality. This means that Mkk is greater than or equal to Mek minus 1, but this implies that Mkk itself goes to plus infinity as k goes to plus infinity. So we have found a sequence of compact sets, subsets of E, such that its measure goes to plus infinity. So then again we have that the measure of E is the limit or the supremum of subsets of E, compact subsets of E, Mk, because the right hand side is again now infinity. So this proves our inner regularity property. Now the last lemma is the so called dominated convergence theorem convergence theorem for sets, for Lebesgue measurable sets. Lebesgue measurable sets, which is the following. So this states that if F is a Lebesgue measurable subset of Rd with finite measure, which is that MF is finite, and we take a collection En, n equal to 1 to infinity, of Lebesgue measurable subsets, such that each of these En is a subset of F for all n greater than or equal to 1, and we assume further that there exists a set E, subset of Rd, such that the indicator functions of these Ens converges pointwise to the indicator function of E as n goes to infinity. This means that the limit as n goes to infinity, chi E n x is equal to chi E x for any x in Rd. So if we assume further that the indicator functions converge pointwise to E, then E is Lebesgue measurable. This is the first part of the claim, and the measure of E is the limit as n tends to infinity of MEN. So this is called a dominated convergence because of this domination by this set of finite measure F, and we will see that this is a special case for the dominated convergence theorem for the Lebesgue integral, which we will see later. So the domination part comes from this Ens being a subset of a fixed Lebesgue measurable set of finite measure, and the convergence holds that when you take the limit of the measures of Ens, it converges to the set E for which there is a pointwise convergence of the indicator functions of En. So let's see how we prove this. So first I claim that lim sup as n tends to infinity of these functions chi E n x is nothing but chi of the lim sup of En as n tends to infinity. So the lim sup of the indicator functions is the indicator function for the lim sup of En. Similarly, lim inf as n tends to infinity chi E n x is equal to the indicator function of the lim inf as n goes to infinity at x. So I'll just prove the first one, and the second one is quite similar. So once we have this claim, so if chi E n converges to chi E as n goes to infinity, this implies that lim sup of En equals lim inf as sets of En as n goes to infinity is equal to E itself. So this is because pointwise convergence means that lim sup lim sup of these functions chi e and x is equal to lim inf chi e and x is equal to the limit of chi e and x, and this is chi e x. And because this is both the lim sup and the lim inf, lim sup en, so we have an equality of indicator functions for two sets. This implies that E is equal to lim sup en equals lim inf en, because since chi a x equal to chi b x is the same as saying that a equal to b. So I am using this fact here because we have two sets E and lim sup of ENs and the indicator functions are the same. Therefore the sets themselves will be the same, and similarly one can do this for the lim inf. So we have these three equalities that follow from this claim. So let me prove the first one for the lim sup, and let's see how this is proved. So first let me recall the definition of the lim sup of the function chi e lim sup of chi e and x. This is by definition the limit as n tends to infinity, the supremum of k greater than or equal to n chi e k x, and this sequence, this is a non-increasing sequence, so monotonically non-increasing sequence of numbers. So this is also equal to the infimum of all n greater than or equal to 1 of the supremums k greater than or equal to n chi e k x. So this can both be taken as the definition of the lim sup, and so now we have to show that this lim sup is equal to the indicator function for the lim sup of the sets En. So now let x belong to the lim sup of En and tends to infinity. So this is the same as saying that the indicator function has the value 1. So because it belongs to the lim sup of all Ens, this implies that there exists, so for each n in n, there exists n prime greater than or equal to n such that x belongs to En prime. So for each capital N, we will find a bigger n prime such that x belongs to En prime. So this follows directly from the definition of the lim sup. Remember that x belongs to infinitely many elements of the lim sup. So if you take any finite n, then there always exists n prime greater than that n such that x belongs to En prime. So this implies that the supremum of n greater than or equal to n prime of this chi En x, or rather k n greater than or equal to n chi En x, this is going to be 1 because the indicator function is bounded above by 1. Indicator function of any set is bounded above by 1 and bounded below by 0, and so if it belongs to En prime for n greater than n prime greater than or equal to n, so it will assume its maximum value, and so the supremum will be that maximum value 1. So this is true for any capital N. So therefore this implies that if you take the infimum over all capital N greater than or equal to 1 of these supremum values, n greater than or equal to n, capital N, chi E n x, so each one this is equal to 1. So therefore the infimum is also equal to 1, but this is nothing but the lim sup as capital N goes to infinity of these numbers chi E n, capital N x. So this is equal to 1. So in this case we have proved that this lim sup is equal to the lim sup of E n of x. So when the right hand side is 1, the left hand side is also 1. Now I am going to prove that if the right hand side is 0, then the left hand side is also 0. So because the indicator functions takes only these two values, our analysis is easier somewhat, that we only have to check for these two values 0 and 1. So now let that the indicator function of the lim sup E n, this is 0. So this means that x does not belong to the lim sup of this of En's. So this is equivalent to saying that x belongs to only finitely many En's, because the lim sup is by definition the set for which x belongs to infinitely many such En's. So if it does not belong to the lim sup, then x belongs to only finitely many En's, and this implies that there exists n naught belonging to the natural numbers such that x does not belong to En for all n greater than or equal to n naught. So after a fixed finite value n naught, x does not belong to any other En's. So this implies that the supremum of n greater than or equal to n naught of chi E n x is equal to 0, because it does not belong to any of the En's, so it will take the value, constant value 0 after n naught, which means that because these values for the indicator function is bounded below by 0, this also means that the infimum over all n of the supremum over all k greater than or equal to n chi E n ekx, this is also 0, because after n naught it takes the least value possible. So when you take the infimum over all n, then it must be 0, and this is nothing but again the lim sup n goes to infinity chi E n x. So we have shown that when this is 0, when the indicator function for the lim sup of the sets is 0, then the lim sup of the indicator functions is also 0. So we have shown that lim sup, this implies that lim sup chi E n x is equal to chi lim sup E n x. So for all x in Rd. So similarly one can show that the lim inf n goes to infinity chi E n x is equal to chi lim inf E n goes to infinity of x for all x belong to Rd. So this, you can view this as the justification of calling this set lim inf, because we defined it, or even lim sup, we defined it using unions and intersections, but this is somewhat a justification for calling them lim sup and lim inf, which is not evident from the basic definition of lim sup and lim inf. So in this way we have identified the indicator functions. So this implies that if limit n tends to infinity chi e n x exists, then lim sup of n equal to lim sup of n tends to infinity chi e n x is equal to the lim inf n tends to infinity chi e n x. Both of these are bounded and the limit exists precisely when these two are equal. So therefore this implies that chi of the lim sup of E n x is equal to chi of lim inf of E n as n tends to infinity, and by the hypothesis this is also equal to the chi e of x. So we have three indicator functions for three different sets: lim sup E n, lim inf E n and E. But indicator functions are the same, means the sets themselves are the same. So E is equal to lim sup E n is equal to lim inf E n, and this is why E is Lebesgue measurable, because the lim inf and lim sup of measurable functions are Lebesgue measurable. So E is itself Lebesgue measurable. So now we have to show that MEN converges to ME as n tends to infinity. So we are going to use the upward monotone convergence theorem. So we will use the upward monotone convergence theorem as follows. So for this we define for each n greater than or equal to 1 Fn to be the intersection of all the EMs. So this is a Lebesgue measurable set. Fn is Lebesgue measurable, and we have F1 is a subset of F2 is a subset of F3 and so on. So it's a non-decreasing sequence of nested Lebesgue measurable sets. So therefore if you take the union of Fn's n equal to 1 to infinity, this is nothing but the union of the intersections EM, and this is exactly the lim inf as n tends to infinity of ENs, and this we know that this is E. Therefore by the upward monotone convergence theorem, we get that MFN converges to M union Fn n equal to 1 to infinity, and this is ME